This video lecture is about inequalities. We have seen already Chebyshev's inequality, and we have seen Markov's inequality for probability spaces. And now we stay in probability spaces, and we're going to discuss Jensen's inequality. Before we can state Jensen's inequality, we need to define what is convex functions, because a convex function is the object of Jensen's inequality. For a function to be convex, it is a 3-point condition, unlike for a function to be increasing or decreasing, where it is a 2-point condition. What do I mean by that? I mean, if we take 3 points in the domain of the function, let's call these points x and y, the extreme points, and a point in between that interpolates between x and y, and we look what are the values taken by the function f on these extreme points x and y, then the function in between 2 points, the function will have a value, will take a value which is lower than linear interpolation between these points. This is what it means for a function to be convex. For any pair, for any triple of points, the one in the middle, the function there will be lower than what would be the segment, the linear segment connecting these 3 points. So this is what a convex function looks like. And what Jensen's inequality says is that if when x is an integrable random variable and it takes values on an open interval I, or you can think for many purposes, I can be the set of positive numbers, can be the set of all real numbers, it just has to be an open interval. And we define a function f on that interval to be a convex function. So we're applying now this function f to the random variable x. So it's good that x is taking values in the domain of f, so we can talk about what f of x means. Then Jensen's inequality says the expectation of f of x is larger than f of the expectation of x. And how can we prove this inequality? Well, the main step in the proof, it has little to do with probability theory or measure theory. It is a property of convex functions that I will just pull out of the hat, and without much justification. It just comes from analysis. So here's a proof. And the proof is the following. A function being convex, f being convex, it implies that for every point, let's call this point x in the interval I, there exists a constant c, a real number c, okay, that c depends on x, of course, such that f of x plus z is more than f of x plus c times z for z, as long as z plus x is in the interval I. So this is really saying a function being convex means for every point x there is a number c, and c is the slope of this line, such that the function stays above this line. C is the slope of the line. This is what this inequality here is saying. And now, to prove Jensen's inequality, we just need to apply this property of convex functions to a point x. Here, instead of x, we can put the expectation of the random variable x, and this will become f of the expectation of x plus whatever number will be f of the expectation of x plus a constant times that number. And now that number Well, we can define here a random variable to be, let's call this x. Okay, we can always adjust z to be equal to z minus the expectation, x minus the expectation of x. So if we define z this way, because c is fixed, and this inequality is true for every z, then what we get is that the function f evaluated at the random variable x will be always bounded from below by f of the expectation of x plus this constant c, which is a finite constant, again, times x minus the expectation of x. And we have already seen in a previous exercise that the expectation of this part here is 0. So we have this inequality. We know that expectation is monotone. So this inequality implies also inequality for the expectation. This is a number. So expectation of a number is just a number. The expectation of this part is 0. So this gives us exactly Jensen's inequality. This concludes the proof.